Hey guys, all right. This is going to be the last lecture for today. It's going to be an introduction to chapter 16. Know that this will not be on your test Wednesday. Let me say that again. This will not be on your test Wednesday. Okay? But we still need to talk about a few more things. So let's talk about acids and bases, all right? We've already introduced these, and we introduced these last semester, right? At the end of last semester. We talked about the fact that acids, right? Acids come from the Latin word for sour or tart. Comes from the word acidus. Okay? Acids are really cool. They have the ability to dissolve metals and produce hydrogen gas. You did a lab on this where you got to shoot little rockets, right? Pretty cool stuff. Um, and acids have the ability to neutralize bases and vice versa, right? And we can measure their acidity with litmus paper, pH meters, indicators, a lot of different ways, right? There's all different types of common acids. Hydrochloric acid, this is stomach acid, right? You've got your acids here used in fertilizer or explosives because there is a very big connection between fertilizer and explosives. Phosphoric acid, if you've ever had a Coke, you've drank phosphoric acid. And then you've got like your citric acid, carbonic acid. If you've ever had a carbonated beverage, you've consumed carbonic acid. And if you've ever had any vinegar before, like a vinegar sauce, you've consumed acetic acid. Okay, so acids aren't necessarily bad. That's the main thing. If you get nothing else from this chapter, the one thing I want you to get is this: get out of your head that acids are bad and bases are good, because that's a very, very dangerous misconception. Strong acids are bad and strong bases are bad. It's weak acids and weak bases that are safe. Okay? It has to do with weak, not the fact that it's an acid or a base as to whether it's bad or okay. Right? Bases, they have a bitter taste. And for the most part, we use bases for cleaners, right? They feel very slippery to the touch. It's basically soap, right? And bases can neutralize acids. And some medicine, so if you have acid reflux disease, you may take like milk of magnesia or chew up some calcium carbonate tablets or something like that because you're going to consume a base to react with the hydrochloric acid in your stomach to perform a neutralization reaction so that you have less acid in your stomach. Okay? So we talked about one theory of acids and bases last semester, and that theory was the Arrhenius theory, right? This is the same guy who popped up in chapter 14, right? Arrhenius. But so he was able to link the behavior of protons and hydroxide ions to acid and base behavior, right? So he defines acids as things that increase the concentration of protons when dissolved in water. And bases are things that increase the concentration of hydroxide ions when dissolved in water. And notice the different terminology here. I'm saying molecular acids because all of your acids are molecules, meaning they do not contain metals. They are molecular compounds. Okay? And molecular compounds, we say that molecular compounds ionize, whereas some of your bases are molecular and will ionize, but a lot of your bases are ionic, meaning they have a metal and then a non-metal contribution. And so ionic substances dissociate, right? But and we talked about how, if it's a strong acid, it's going to completely dissociate. There are 7 strong acids. If you forgot them, you need to review them, right? You have one of your strong acids is what we say is polyprotic. Specifically, it's diprotic. It has 2 protons. That's sulfuric acid. There's also hydrochloric, hydrobromic, and hydroiodic acid. And then your remaining 3 acids are nitric, lost my pointer, nitric, chloric, and perchloric acid, right? And a strong acid is a one-way arrow because it completely dissociates into protons and anions, but a weak acid gets an equilibrium arrow because it only partially ionizes into protons and anions, and you're going to have some acid that hasn't dissociated as well in that equilibrium. So you're going to have three substances in the equilibrium. Whereas if you put a strong acid in water, you just get ions. You don't have any acid left. And there's a different way that we represent protons as far as chemistry is concerned, because a proton is an H plus ion. Why do I call an H plus ion a proton? Because hydrogen is one proton and one electron. And when it loses its electron, it becomes the H plus ion, right? It becomes just a proton because it's lost its electron. And so what happens is that proton can interact with a water molecule and form something that we call hydronium, okay? And what hydronium is it's literally water where the proton has attached itself to one of the lone pairs, and it becomes H3O plus, because you had H2O plus H plus is H3O plus. So this is what it looks like in the Lewis dot form. And as far as I'm concerned, these two are essentially interchangeable. Okay, we use them interchangeably in reactions all the time because remember, water is a pure liquid and doesn't appear in a K expression. So a lot of times we ignore the fact that water is present and just say an H plus when in fact it's actually hydronium. It just doesn't really matter. All right, they're interchangeable. And we talked about neutralization reactions that happen, right? That when you take an acid, specifically a strong acid and a strong base, and you add them together, you're always going to make two products. And those two products you're going to make are water and a salt, right? Water and a salt. And a salt is defined as any ionic compound whose cation comes from the base, there you go, and whose anion comes from the acid. So if you want to make table salt, which is sodium chloride, you need to take hydrochloric acid and react it with sodium hydroxide. What if you needed potassium and you needed to take like potassium chloride? Well, then take hydrochloric acid and react it with potassium hydroxide, right? So you can swap out the acid and the base to generate several different salts, right? But here's the problem. So this theory, everything we've talked about so far should have basically been review for you. But the problem is the reason why we have to learn new stuff and why there's a whole chapter dedicated to acids and bases is because the definition's not good enough. Not all bases generate hydroxide ions, and not all acids have protons and generate protons. So how are we supposed to identify acids and bases? Basically, what we learn is this. The Arrhenius theory is the most specific theory of acids and bases. What we need is a broader theory, right? We need a bigger, broader, new theory, okay? And what's really kind of cool is that two scientists at the same time back in 1923, you have Danish chemist Johannes Bronsted, and then you had the English chemist Thomas Lowry. And in 1923, they both published the same theory independently, which is kind of cool. That happens sometimes in chemistry. So we call this the Bronsted-Lowry theory because we're trying to give them both credit because it's both their ideas, right? They did it separately, but it's both their ideas. And the idea is, so they still define that acids need to have protons, but they just look at it from the proton perspective. They say that acids are proton donors, which means they have to have a removable acidic proton. We'll talk about what it means to be an acidic proton as we move forward in this chapter, but it basically means the hydrogen needs to be attached to an electronegative atom. Like it has to be a polar bond, and what it's attached to needs to be way more electronegative than the hydrogen because The CH bond is a nonpolar bond. That's not an ionizable proton. That's not a removable acidic proton, right? But a hydrogen attached to an oxygen is, right? Because oxygen's super electronegative. So acids are proton donors. Bases are proton acceptors. But remember what a proton is. A proton is an H plus ion. It has no electrons. To generate a covalent bond, you need 2 electrons, which means your base must have a lone pair on it, right? The base has to have a lone pair. That's the only way it could accept the proton. So here you have your acid, here you have your base. The acid is going to donate the proton, so the H plus comes off and attaches to the base to become HB plus, right? This is just an example, right? So here's your, this is what you formed. And then once this loses the H plus, it becomes a minus. So we have some substances like water, and this is honestly why all living planet or planets with living substances have to have water, is because water is a super cool substance. It's what we call amphoteric. Okay, amphoteric. So the pH makes an F sound. Amphoteric. And amphoteric substances can either be an acid or a base. So look at water. Water has a lone pair on it. So it could accept a proton. And if it accepts a proton, it becomes hydronium. We already talked about that. Or it could donate a proton, and if it loses an H, then it's just OH. But remember, it gets to keep the electron, so it becomes OH minus. So it can form hydroxide. So it depends upon what you put in the water as to what water decides to act as. So if you take an acid and you add it to water, then water is clearly going to be a base, right? The acid donates the proton to the water and you form hydronium, and in this case, the chloride anion. But if you add ammonia to water, ammonia is a weak base. So then water would act as the acid. Water is going to donate the proton to ammonia. So ammonia becomes ammonium, and water becomes hydroxide. So you get sort of water can choose to be what it wants to be. All right. So, and the really cool advantage of the Bronsted-Lowry reaction, and maybe you noticed this and maybe you didn't, is that when this proton transfer happens, what happens is you end up generating an acid and a base on the product side as well. So when the acid donates its proton to the base, it forms what we call the conjugate base because it now has a lone pair. It could now accept a proton. It creates a base. Whereas the base, when it accepts the proton from the acid, it creates a conjugate acid. It creates something that could donate a proton. So what it means is this is a perfect way to write a reaction that's in equilibrium. Because if it's in equilibrium, it needs to be able to be reversed. And this absolutely can, because you've got an acid and a base on the left, and you have an acid and a base on the right. So we can absolutely flip this thing as many times as we need to, right? So if we go back to our ammonia and water reaction, if we take ammonia and we react it with water, this is a base, which means water would be the acid. Water is going to donate a proton, and the acid forms then the conjugate base that is hydroxide. And when ammonia accepts the proton from water, it forms ammonium and becomes the conjugate acid. And so that's the concept of conjugate acids and bases. We will pick back up with this concept on Friday because Wednesday is your test. on 14 and 15, not this.